new? We have these bright new lights. I'm going to need shades in the class.
Hi, Dr. Roger.
Morning, Jeffrey. Okay, guys, get your name tags out just so I know who you are. Otherwise, I'm going to ask this lady what her name is.
I lost my name tag a long time ago, so.
Yeah, well, I know your name because you're always very noisy. All right, where's the rest of the class? I hope they're on Zoom. Guys, you know, you're supposed to be here. It's very uninspiring to teach an empty classroom, even though the rest of you might be on, you know, somewhere on the cloud. As it happens, even my TAs are kind of late. Okay, everyone, the usual stuff, please. The attendance poll is number 623. And let's begin. That's 8 a.m., right? So please shut your laptops, turn your phones over, the usual good stuff. I'll wait for you. You're not able to find 623? Are you sure? Okay, the others have found it. Okay, do you find it, Akshara? Okay. All right, folks. I'll give you a few seconds to settle down with the attendance poll, and then let's start. Mohammed. Don't forget to have your name tag out. You know, it's tradition. All right, guys. That's 8:01. Let's begin. We're going to. So the story so far, we've seen that MLPs are universal function approximators. What did we mean when we said this? When we said MLPs are universal function approximators. Anybody want to reply? Mara? No. So what do we mean by saying they're universal function approximators? Yes.
If we have at least one hidden layer, we can, in theory, make it as wide as possible, such that we can, like the layer as wide as possible, as many nodes, such that we can approximate a function.
So it's actually even simpler than that. The one hidden layer is just, uh, is, uh, is saying that even if we have only one hidden layer, the more general statement is this: regardless of the kind of function you give me, I can always construct a neural network that actually computes this function to arbitrary precision. And that's about capacity, right? What it can do, but then it has to actually be trained to compute this function, and we saw that this could be done through variance of gradient descent. And the kind of models we've seen so far where feed-forward networks, multi-layer perceptrons, where one layer of neurons feeds its outputs to the next layer and so on until you get a final output. So these can recognize patterns in data. But here's a new problem. I work on speech. And so one of the early problems we had was something of this kind. Wake-up words. Does this segment of signal include the word welcome? So what we would typically do is slice out a 1 second segment of the signal and pass it through the classifier. So if I want to do this, the simplest thing for me to do is to first convert it to a spectrographic representation, which you have worked with for homework 1. And then subsequently, how would I actually build a welcome classifier? I have lots of examples of segments with the word welcome in it, lots of examples of the segments without welcome. How would I train? What kind of a classifier would I learn based just on what we've seen so far? Anybody? I can just train a simple binary classifier, just stick an MLP on the whole thing. And the MLP's output is either going to be a 1 or a 0, depending on whether the word welcome is in the recording or not. But then here's the situation. In one recording, the word welcome occurs on the left within my 1 second segment. In the other, the word welcome occurs, but it's somewhere to the right. Will a network that is capable of recording and identifying the word welcome when it occurs on the left of the recording necessarily also succeed when the word is to the right, when the position has changed? Why not?
It's not indicate on the instance that would recognize.
So basically, the two are very, very different in the feature space. So if I think of my entire input as an elongated vector, then I have a vector of this kind. In the first case, stop going up. Okay, the word welcome occurs over here. So if, for instance, I had binary features, just a second, Jeffrey, then all of these would be 0, these would be 1, these would be 0, because this is where the word welcome has occurred. In the other case, the word welcome occurs here. I have 1s over here and 0s elsewhere. The two live in completely different subspaces, right? And so that's like in the dimensions 3 and 4. The next one is in the dimensions, I don't know, whatever it is as the board goes up. So the one that recognizes the first will not recognize the other. What we need is a simple network that will fire regardless of where the word actually occurs. And it should not fire when the word doesn't occur at all, right? Same thing with pictures. Here are a collection of pictures with flowers in them. And this question is there a flower in any of these images? So here I have these two images. If I decide to build an MLP to detect flowers, I could just train it with images that include flowers and images that don't. But then an MLP that can detect a flower if it occurs in the top left corner is not guaranteed to detect it if it occurs in the bottom right, for the same reason as what we have in the board up there. And once again, we have a situation where we want the network to fire regardless of the location of the pattern. So what we need is shift invariance, where the location of the pattern doesn't matter, only the presence of the pattern matters. And conventional MLPs are sensitive to the exact location of the pattern, so they will not work, right? Yes, Amit.
So looking at the phonemes approach that we use, why would this be a problem? Because it would still be able to identify the phonemes associated with it.
So in the first case, the phoneme occurs in the dimensions 3 and 4. In the last case, the phoneme occurs in dimensions, say, 27 and 28. Are they the same thing? So is the vector 1, 0, 0 identical to the vector 0, 0, 1? It is not, right? Yes, Jeffrey.
Is it something like the MLP has like a phoneme detector, and like basically the MLP has this like a special little like thingy for every like dimension, and it has a special phoneme detector in like the dimensions where like the phoneme would occur in training data, but like when the test data comes along, since like for that dimension, like it's empty, but for another dimension, like the phoneme's there, then it doesn't see it because like it doesn't trigger the detector.
That's pretty much it, right? Yes.
This is why context solves the problem. Like,
Context will not solve the problem. You just shifted it to a different dimension altogether. It's in a completely different subspace. In one case, the pattern is in XY. In the other case, the pattern is in YZ. They're not the same pattern, right? So how would you solve this problem? How would you solve the problem of shift invariance? Anybody? Yes.
A very brute force and probably crude method that I don't know if we're going to talk about. It's like we just guess at each point. We start the ML, like the neural network at each point in the sequence.
We could scan, right? The simple problem is, solution is I'm going to train with the word welcome at every possible position. But if I train with the word welcome at every possible position, how many options do I have? Too many. And to capture all of them, my network must become very large, and the amount of training data I require is going to be enormous. On the other hand, I can do, I forget your name.
Ryan.
Ryan. Okay. Thank you, Ryan. So we can do what Ryan just suggested. We can scan. I can have a little network which can detect the word welcome and then scan the entire input end to end to find out if it fires anywhere. So I'm going to get an output. So here's the complete sequence of classifications. I'm going to get one output at every location. And then if I get an output at every location, my question is there a word welcome somewhere in this recording? How do I combine all of these to get a single output for the entire recording? Yeah.
One idea would be taking the max of all of them, if any of them like outputs one, or I guess you could say there might be like an underlying like distribution because you start at like elcum and then locum and so on.
So that's right. So just taking a max is going to solve it, right? It's an OR. A max is an OR. If any of them has the word welcome in it, it's going to fire. And so at least one of these outputs is going to be high. And so taking a max, if the max is not close to 1, the word welcome hasn't occurred anywhere. Instead of having a max, I could use a perceptron or a more complex network, as Ryan just mentioned, to capture a little more complexity in the pattern. So here's how the code for it would look. You're going to be going across the input. At each portion, you pull out a segment, which is approximately the width of the word welcome that you expect. You classify each one of these. And then finally, you take the classification outputs at each position and put it through a softmax or any other kind of processing. So this is the entire processing. But then if you look at this entire thing is just one giant network. I have some MLP-like structures analyzing the input at every point. Their outputs are combined and then going through yet another MLP. It's just an MLP, right? What's the distinction? What's the difference between an MLP like this and the standard vanilla MLP? Yes.
Is it true that the difference between this one and the crazy one you suggested is that for the crazy one, you have to like relearn the MLP each time, and for this one, you can like slide the same MLP over each window?
That is one, but then there's a structural difference. And what is that? Anyone? Yeah.
All of the individual scans should be the same.
So this is the restriction that it's a one giant network. It has many subnets, and all the subnets are identical, right? So that's the key difference. So this is just the final layer of the overall MLP, but this entire thing is just one giant MLP. I can do the same thing with pictures, right? So I can have a little picture detector, which looks at a window of the input to detect if there's a flower in it or not. I can scan the entire input top to bottom, left to right. And then when I have an output at every position, I can take the collection and put it through a max or a softmax or another MLP. And this is going to give me a shift invariant pattern detector because it doesn't matter where the pattern occurred, you're going to find it. Yes, Ryan?
So we're taking the full pattern. We're not just taking the max, because if we took the max, then we wouldn't be able to account for different sizes of objects. In this case, like if a flower is a little.
So we're assuming that the size is kind of fixed, right?
Okay.
Right, we're looking. You're right. Yes. We'll get to that later. Okay, but yes. It is going to be sensitive to the size. If you get a bigger flower, this will obviously not find it, or a smaller one. So in the two-dimensional case, here is the situation again. You're scanning it left to right, top to bottom at each point. You're pulling out a little section of the input. You're passing it through an MLP, and you get an output. That collection goes through a softmax, and then you get a decision for the entire input. And of course, this entire thing is really just one giant MLP with identical subnets. So meaning all the lower layer subnets are required to be performing the same processing, because scanning is the same as having many copies of the network, right? And so once we realize that, I can just say this whole thing as one network. That final Y is just the final softmax. It's one giant MLP. Any questions?
Yeah, I have a
Yeah.
question.
Yeah, go ahead.
Now, does this mean the validation set will contain images of just exactly where the flower is located, or you can have images with flowers at all? Like, yeah.
So this entire thing is, I'm not sure I understood your question, but this entire thing is position or shift invariant. Meaning if I took the picture of the flower and moved it to a different location in the image, the output is not going to change. Did that
Now,
answer? Yeah.
will the validation data set just contain patches where, like the exact patches where the flower is located?
No. This is just, okay, so because our question is there a flower in this image? Which means from our perspective, the data that you're going to provide for training are going to be pictures with flowers and pictures without flowers. That's it, right? Without actually marking the location of the flower. Okay, so here's your first problem. For those of you who haven't been observing, we're at slide 47. I'm going to go through 300 slides today. Do we have the... Okay, the Pokemons are back on. Jeffrey, I'm going to need your help. Where are my glasses? Yes. Oh, Persian. Yes. Who's Persian? Is Persian around? Nope. Okay. Who's Ledian? L-E-D. Ledian. Who's Ledian? Okay, first question.
True.
True. Everybody agrees that the answer is true for the first question? Okay. And who's Wingull? W-I-N-G-U-L-L. Is that right?
Wingull.
Uh-huh. Who's Wingull?
Wingull?
Yeah. Okay, second question.
True.
Also true, right? So we can determine if the picture has a flower by scanning for it with an MLP. Scanning for the picture for a flower to determine if the picture has a flower, it's strictly the same as analyzing this entire picture with a single large shared parameter MLP, right? So any questions? We all agree on this so far? Yeah.
I understood the max. What is the point of the softmax?
The softmax is, if you're allowing some kind of a jitter, right, or doing composition by parts. That's it, yeah.
Based on which of those networks have become activated, which of those networks which are looking at different positions, can we also not tell where the flower is?
That's actually, yes, it's an interesting question. Make sure to ask me this question after next week, right? But yes, this is an instance of what's called learning with weak labels. When you learn with weak labels, you're given a collection of data and you're just told, this collection contains a positive instance, or this does not. And then from this kind of labeling, you must determine how to detect the specific instance. So this is exactly an instance of that. So before I continue, I'm going to change my illustration a little bit. Here's how I've been drawing MLPs so far. So if I was scanning with this MLP, if I was scanning this input of 8 time steps with this MLP, and after each position, if it took a stride of two time steps, here's how the scanning would happen, right? And so the entire collection is going to look like this. But when I draw things in this manner, it sort of misrepresents things, because on the original input, the horizontal axis is time. So this sort of gives us the impression that the yellow neurons are computed after the orange neurons in the first layer. That is not true. That entire layer is computed all at once. So a better representation is vertical, which is to say that the first layer is computed from the inputs, the second layer is computed from the first layer, the third layer is computed from the second layer, and so on. We're going to assume that the network is fully connected. So I've shown a whole bunch of arrows, but then I'll use a simpler notation with just a single arrow. So each block represents a layer, And an arrow from one block to the other means that every neuron in the source layer connects to every neuron in the destination layer, okay? And so this visualization is actually going to be drawn like so. This picture making sense to you guys? Right, yeah.
So it's supposed to just make it easier to read, or?
So it's not just making it easier to read, it's also conveying the impression that this entire computation is done at one time. Whereas if I drew it like this, it seems visually, it conveys the impression that you're computing these things left to right. So the orange neuron is computed first, and the red is second, and the yellow third. That's all.
Okay.
Right? This is just to say that every bar represents one computation at one instant of time. Okay? So this is, if I were analyzing the input with a stride of 2, this is what the computation looks like. With a stride of 1, so here you go. This entire bar computes, analyzes these 2 inputs. Then the entire bar analyzes these 2 inputs, and so on. So here's the actual computation. Is the illustration making sense to you guys? I'm going to use it a whole lot, right? Okay. So now going back, so in our problem, we saw that these are just really large networks, whether you're scanning for flowers or whether you're scanning for the word welcome. And we can use conventional backpropagation rules to train the network, but there's a caveat. And so how would we use backpropagation rules over here? Again, our question is, does this picture contain a flower, or does this recording contain the word welcome? So we're going to be presenting lots of examples of pictures with flowers and pictures without flowers, or recordings with and without welcome, and you must train from them, right? And then you can just use gradient descent as before. But then the issue is that these subnets are all identical, or in this case, each of these vertical columns represents an identical subnet. Every column has the same parameters as every other column. So if you use gradient descent to modify the parameters of this subnet, those modifications must be instantly reflected in every copy of that subnet all the way upwards. Making sense, right? So how do you change the gradient descent math for this? It's kind of simple. Here's a trivial example. Let's say these two edges have the same weight. So, it's one of the weights of, say, a column over here, right? So if within a network, I decide that these two edges have the same weight, it means that this weight, which I've represented as Wkij, is the same as this weight, which have represented as Wlmn, and the common value is W subscript S. That's what I mean when I say that these parameters are shared. I have these 2 parameters, they're forced to have the same value. So for any training instance X, if I perturb Ws a little bit, it means each of these guys is perturbed by the same amount. And so, any perturbation of the common value is going to perturb both of these values. And each of those perturbations is going to eventually influence the divergence. So when I draw the influence diagram, this is what it's going to look like. The common value Ws influences both Wij(k) and Wlmn. Each of them, in turn, influence the divergence. Now, when I'm learning the parameters of the network, I'm trying to learn Ws, because that can be copied into the 2 weights that have the same value, right? So what is the derivative of the divergence with respect to Ws? Now, without looking at the slide, if I have something of this kind, say dive, I'll call this W1, W2, and this is the common value Ws. What is the derivative of the divergence with respect to Ws? Without looking at the slide, can someone tell me? Yes, Riti.
The derivative with respect to W1, then W1 into Ws, and the same with
W1,
and then W1 into W by Ws, and the same with W2.
so we are computing the divergences, the derivatives down both these paths, and we're adding them, right? Now, specifically, if W1 is defined as being identical to Ws, what is the derivative of W1 with respect to Ws? 1. So that means this goes away, and so also this goes away. And so you just say the derivative of the divergence with respect to Ws is simply dW1 plus dW2, right? Easy enough. Nothing complex about this arithmetic. Once you realize this, you just know that when I have a network of this kind with many parameters which are supposed to have a common identical value, I want the derivative of the divergence with respect to this value. And that means I need the derivative of the divergence with respect to every copy of it. And all of them must be summed up. Not averaged, but summed up, right? And so if I wanted to perform gradient descent to train this network, for every parameter that's shared, I need the derivative of the divergence with respect to that parameter, Ws. And the parameter itself is going to be updated using the standard gradient descent rule. And then the updated parameter can be shared across all the copies. This means that we need to know what is the derivative of the divergence with respect to this shared parameter. And our math just told us that the derivative of this divergence with respect to the shared parameter must be obtained by summing the derivative of the divergence with respect to every copy of the parameter. And observe that these derivatives need not be identical. For example, if the flower is here, but the flower is not here, then this portion of the network will probably have very low derivative because moving it a little bit is not going to detect a flower. Whereas the guys where the flower actually is present are going to be more sensitive. So you're going to add all of these derivatives up. Each must be individually computed. So this term has to be computed using backprop, every one of these derivatives. And once you do so, then the update rule is fairly straightforward. And so here's where we are. Position invariant pattern classification can be performed by scanning in 1 dimension for sound, 2D for images. You can take this to higher dimensional data like 3-dimensional data. Scanning is equivalent to composing a large network with repeating subnets. So the large network has shared subnets. And learning in scan networks requires that backpropagation rules must be modified to combine the gradients from parameters that share the same value. The principle applies in general for networks with shared parameters. This clear to everybody? Any questions? Okay. So we're going to move to the next step, right? I'm going to use this vertical representation over here. And let's say I'm analyzing this recording for the word welcome. So when I analyze this first segment using this recording, this input is first going to be processed by the first layer. And each of the neurons in the first layer is going to generate an output. Then the second layer is going to use the outputs from each of the four first layer neurons over here.
Excuse me, Prof.
Was that a question?
Yes.
Yeah, go ahead.
Say that we have the same weights for, let's say, WMK, like we said previously, on the same subnet is the same. Does it mean that the network is fed from a single point, or it means that the linear combination of the weights at each hidden layer is going to be the same?
So it just means if these two subnets are identical, it would mean that this red edge over here has the same weight as this red edge, right? That's it.
Okay, thank you.
Okay. So anyways, and so the first layer neurons would compute their outputs. Then the second layer neurons are going to compute their outputs from the first layer neuron outputs. And then the third layer neuron is going to compute its outputs from both the second layer neurons. So the 7 circles that I've drawn vertically are the 7 values computed when analyzing this block of the input. Is that illustration making sense to you guys? Yes, no?
Yes.
Okay. So as I stride forward, we would be computing these 7 values in the first position. Then you go forward a little bit and you compute the same 7 values in the second position, and then in the third position and the fourth position and so on until you get all the way to the end. These are all the values that you would be computing when you're analyzing this recording for the word welcome. And then finally, of course, the output of the final layer is going to be put through a softmax. Yes?
How many dimensions does the softmax have?
The softmax is going to have, in this case, as many dimensions as the length of the input, right? Over here, that's.
And so how do you figure out if the word welcome is in there? Like if the softmax has a 1 someplace and 0 everywhere?
So here's the thing. The softmax is just a soft version of a max, right? And so if any one of them is high, that's going to be 1, right? That's it.
Would you still put a max over this, or would you put the label as where the word?
You can just put a soft max, and it's just going to tell you whether the word is present or not. You're not trying to detect where it has occurred. Right. The only question is, does this recording have the word welcome? Like your wake-up word detector. Right? That's it. Okay, so is this picture making sense to everybody? Okay. Now this is important because now, let's say I'm performing the same computation as before, right? Except that now the first layer is in a hurry. It doesn't wait for the subsequent layers to perform their computations. So the first layer computes its four values in the first position. And then without waiting for the second layer, it proceeds to go forward and computes the outputs at every single position, right? And then after the first layer has done its job, the second layer and the subsequent network kicks in. And so the second layer computes its outputs from these four values in the first position. And the third layer computes its output from the output of the second layer. Is the output of the third layer going to be different than in the previous case where the entire network looked at the first block? Yes, no? Can everybody say no? No. Thank you, right? And so this guy doesn't change due to the reordered computation. Yes, Jeffrey?
So first, like, the reason why it remains the same is it because like the dependency remains the same, like those two guys in the second layer, like their like inputs are still the opposite first layer. And is this sort of like basically you're like scanning like each layer, like one layer by layer?
That's all you're doing, right? And so similarly, now the second layer, without waiting for the third layer, can go off and scan the outputs of the first layer. At each point, the second layer neurons are looking at the four outputs generated by the first layer neurons, and then the third layer is going to be doing the same, right? So you get a bunch of outputs, right? So Mohammed, can you just shut your laptop? Yes, thank you. So this reordered computation is not going to change the final output. Yes, no? It's not going to change the final output, right? And so the final softmax will still give us the correct answer for the entire input. So what just happened over here? Here's what happened. Earlier, you were going across time. At each time, you're pulling out a segment of the input. Then you are putting the segment through an MLP. But in the process of putting the segment through the MLP, what were you really doing? At each position, you were going through the layers of the MLP. So this is kind of a little funky, but it's important for reasons that we'll get to. And that is that okay, so when I have the segment, just the first layer neurons are looking at a block of the input, right? So which is why I'm saying Y0 is looking at a chunk of the input, T to T plus K, K being the width of this chunk. And then the subsequent layer is only looking at the output of the first layer at one position, right? So that's why you have the if clause for the first layer alone and not for the subsequent layers. Regardless, so you're going through the layers. The first layer is looking at the chunk of inputs and computing an affine value from it, and then putting it through an activation. The subsequent layers are just reading the output from the previous layer, computing an affine value, and putting it through the activation. But observe that all of the action is within the innermost loop of the entire algorithm, right? So over here, if you have the outer loop over time, then the inner loop over layers. So you're scanning over time, at each time you're going through the layers. If I flip the indices of the two outer layers, would the overall output change? Yes, no? It would not, right? And that's basically what we did in what I just explained. All I did was flip the indices. You'd have the same thing, and so this is what we would do when you're scanning with an MLP. You can actually scan with the individual layers, and the output is not going to change. Same thing in the case of 2D. I can have this MLP, which is looking at a region of the input, and it scans, right? So this MLP is going to sort of scan the input at every position. If I arrange the output in the same order, in the same pattern as the input itself, you're going to get this rectangular map where every dot represents the output of the MLP at a corresponding position on the input. And then you can just put the entire thing through a softmax or a max. But then, as before, if this first neuron of the first layer decided not to wait for anything else and decided that it was just going to process the entire input all by itself, right? The first neuron could go off and compute this entire block without waiting for the rest of the network. In fact, all of the neurons in the first layer could do that, right? So if I do this, now let's say I want to find out if there is a flower in this location. What would I need to do? Anybody? Yeah.
Find the neuron that scans that.
So that's simply going to be these 4 positions because I've arranged them in the same shape as the input itself, right? And so this guy here, this guy here, this guy here, and this guy here. Those 4 could be put through the rest of the network, and it will tell me if there's a flower at the bottom right position in the input. So more generally, if I want to find out if there's a flower here, I just have to pick the outputs produced by the 4 neurons when they were looking at that region and pass them through the rest of the network. So this making sense to everybody? Right, yeah.
So currently we said that it doesn't matter if we go with respect to time and then go through layers. What happens if we go in the opposite direction? Even in the image, it makes intuitive sense that yes, the flower being there shouldn't matter if I scan this way or this way. But with the speech, it would make
it shouldn't make any difference eventually. The direction should not make a difference, right? Flipping the loop. Okay. And so using the same principle, because I've arranged the outputs of the first layer neurons in the same order in the same shape as the input itself, the second layer neuron can now scan the output of the first layer neurons. But observe something interesting. In the case of the first layer neurons, each neuron was looking at a region of the input, but just a single input, right? In the case of the second layer neurons are simultaneously reading 4 values, one from each of the 4 maps, where one from each of the maps produced by all of the first layer neurons to produce their output. That having been stated, now the second layer neurons can just individually go off and scan the outputs of the first layer neurons jointly, produce their own outputs. And now, if you wanted to detect if there was a flower here, all you would need to do is to pick up the outputs of the second layer neurons when they were analyzing the outputs of the first layer neuron that was looking at that location. And you'd get a determination of whether there's a flower over there or not, right? Does making sense to everyone? Right, so easy. And I can recurse this. The third layer neuron can now scan the outputs of the second layer neurons themselves, and then the whole thing, I can just read the output of the third layer neuron at any position to determine if there's a flower in that specific location. There's a reason I arranged all of these outputs in the same shape as the input itself. There's a one-to-one correspondence between the regions in the input and the elements in the maps, okay? And these can be put through a softmax or even a full MLP. Now, once again, so we don't need to, in the case of the final layer alone, we don't really need to organize this as a rectangle. In fact, in this case, it doesn't matter for any of the layers, so let's just skip this slide, right? But here's what happened. You're scanning left to right. In the original case, when I was just scanning with an MLP, I was scanning the image left to right, top to bottom. At each position, I was picking out an image segment and putting it through an MLP. But when I put it through the MLP itself is doing the same thing. It's going through the layers. The first layer is actually pulling out a chunk of the input. Subsequent layers are just looking at one element from the maps of the previous layers. You compute an affine term from the outputs of the previous layer, and then put it through an activation. Again, all of the important stuff is happening in the innermost layer, right? So those two, the 2 lines shaded in blue, they represent the scanning. The one in yellow represents going through the layers. If I reorder these, this should not change the final output of the network, right? And so this is basically what we just did. Here's the reordered computation. Any questions? Questions? Okay. And so position invariant pattern classification can be performed by scanning the input for a target pattern. Scanning is equivalent to composing a large network with shared subnets. The operations on scanning the input with a full network can be equivalently reordered as scanning the input with individual neurons in the first layer to produce scanned maps of the input, and then jointly scanning the map of outputs by all the neurons in previous layers by neurons in subsequent layers. I'm emphasizing the joint in that the third layer neurons are going to be looking simultaneously at the maps produced by all the second layer neurons and so on, right? Here's the problem. Okay, I think we have enough time. Who's Squirtle?
Squirtle.
Who's Squirtle? Squirtle around? No, Squirtle's absent. Who's Dragonite? Is Dragonite around? Oh, Dragonite is absent. Who's Muscarian? Masquerain? Masquerain? Oh, wow. The name's complicated and the person's absent. Nice. Okay. And who's Ratata? Ratata is absent also.
I'm online.
All right. Okay. So what is the answer to the first question?
I guess true.
All right. Let's check. But first, let's try the second question. Who's Arcanine? Who's Arcanine? We're having tremendous luck with not finding you guys today, right? So who's Magneton? It's telling me that 70% of the class is absent today. Okay. And who's Makuhita? Yes. What's the second one's true? Okay. Let's see. Scanning an input image with an MLP is mathematically equivalent to first scanning it with the individual neurons in the first layer, and then scanning the output maps of the first layer with the rest of the network. This is true. This operation can be recursed. Scanning the output maps of the first layer with the rest of the network is equivalent to scanning first layer maps of the second, then scanning second layer maps of the remaining network. Also true, right? So far, so good. So what do the neurons in the individual layers actually do? This is where things begin to get interesting. So first, the entire MLP is looking for a flower-like pattern, right? But then the business of looking for flower-sized features is the responsibility of looking for flower-sized features is entirely taken up by the first layer neurons, because it's only the first layer neurons that look at the entire flower-sized region of the input. Subsequent neurons just work on whatever features the first layer detected. So there's a tremendous amount of responsibility on the first layer neurons. If you want this to work, you want to have the first layer to have many neurons, simply because the different ways in which flowers can be presented can be very large. So this is a bit of a problem, right? Yeah.
Why are there 4 output channels again? Is it in the first layer?
There are four neurons in the first layer, right? So each of them is generating a map.
So we slide each of the 4 neurons over the image, right?
Yep. Okay. So here's a different way of doing it. Instead of having the first layer neurons look for flower-sized features, let's have them look for smaller features. Guys at the back, can you shut your laptop, please? Right, okay. Again, as always, you're welcome to open your laptops, just go outside, finish your job, and come back, okay? So we can have these neurons look for smaller features, like say the size of a petal or the size of a sepal, and then scan for these smaller sized features. So now each of the first layer neurons are looking for smaller features, than the entire flower itself. But then the second layer neuron now has to look for flower-sized features. So it can actually look for over a region of the map produced by the first layer neurons. In so doing, what happens is that this neuron is considering every portion of the input that was used in computing any of these 9 values. So the second layer neuron is in fact looking at the entire flower-sized region. This making sense to you guys? Right, okay. And so this effect effectively evaluates the larger window of the original image. So here's what the second layer neuron is doing. The second layer neuron is now looking at the flower-sized region, not the first layer neuron. So what we have done is we have distributed the pattern over 2 layers. Earlier, we were looking for flower-sized features entirely using just the first layer neurons. Now the responsibility for finding flowers has been spread across 2 layers. And so this, what does the second layer neuron learn? Now the first layer neurons are going to begin looking for sub-flower size features like say petals and or sepals and so on. And so now the second layer neuron can say that this guy will fire if, you know, the first neuron in the first layer has found a petal in the left 2 in the left 2 positions. And if the second neuron has not found a petal in the top right position, say, right? And if the third neuron has found something that looks like the stamen in the middle, and if the fourth neuron has found something to the bottom right, you can actually, the second layer neurons are going to compose patterns from the outputs of the first layer neurons, right? Now the second layer neurons can go ahead and scan the output maps of the first layer neurons, but once again, they're going to be scanning all of them jointly. And so then they can produce a map themselves at the various positions. And now, if the third layer, if you want to find out if there is a flower in the top left position, you just have to pick up the values produced by all the second layer neurons when they were looking at the top left position, which is going to be, you know, when they're analyzing the little regions in the red boxes in the output maps of the first layer neurons. And that's going to tell you if there's a flower in the top left position. That makes sense to all of you guys? Right, okay, yeah.
How do we reduce the size of the features that we're looking at? Is it just adjusting the index in the...
That's just going to be adjusting the size of the window itself. We'll get to that later in the class, okay? Or in a subsequent lecture. And so now the second layer, I can have the third layer neurons just scan the output maps of the second layer neurons as before, and you know, their outputs can be put through a softmax to generate the final classification output. Now, although I'm doing all of this, I've distributed the pattern over 2 layers, it's still just a scanning MLP. We began this class by saying I'm going to scan the input for a flower using an MLP. When I distribute the pattern over 2 layers, this did not change. I still have an MLP that is scanning the input. All that happened is that the MLP that's scanning the input itself has shared parameters. Earlier, when I scanned with a single MLP and just combined all the outputs into a single output, it was like having a giant network with shared parameters. I'm recursing the idea 1 step down and saying that even the MLP that's scanning the input has shared parameters. How so? So let's look at the simple example. 3 neurons in the first layer, 2 in the second, 1 in the third. So this first layer neuron might be computing this map, right? This is the black neuron, the red neuron, and the blue neuron. So when the second layer neuron considers this 3 cross 3 region in the outputs of the first neuron maps, then it is effectively considering these 9 outputs which have been obtained from each of these 9 locations, right? And so here is the computation performed by the second layer neurons. The second layer neuron is now looking at 27 inputs. 9 from the outputs of each of the neurons. But how many independent sets of parameters do I have over here in the first layer? Anyone? Dhriti has got the answer. How many do I have? Only 3, right? Because these 9 outputs were all obtained using the same black neuron. These 9 outputs were all obtained using the same red neuron. These 9 outputs were all obtained using the same blue neuron, right? So although the second layer neuron is getting 27 outputs, only 3 independent sets of parameters were used to compute these guys. And now it is this MLP that's scanning the entire output, entire input. That making sense to you guys? Right, okay. And so instead of distributing the parameter over 2 layers, I can distribute it over 3 layers, exactly as before. So now the first layer neurons could be looking at even smaller regions to produce their outputs. The second layer neurons could be looking at small regions in the maps of the first layer neurons to produce their outputs. So here the second layer neuron, if it's looking at this 2 cross 2 region, it's effectively, so the first layer neuron is going to be looking at regions about the size of this box. So if the second layer neuron is looking at this set of 4 neurons, it's looking at any region of the input that was used in computing any of these 4 values. So it's looking at the slightly larger region of the input, right? And the second layer neuron would now be, and now the maps of the second layer neuron can be read in a similar manner by the third layer neurons, right? And so what the third layer neuron is doing now is looking at any region of the input that was used in computing any of these 4 values of the second layer maps, which is basically any of the regions shown in red in the first layer maps, which corresponds to that entire input. So you can see how we have actually sort of spread the features that we are looking for, the patterns that we are looking for across multiple layers. Does this make sense? Now, unlike the previous case where I was just reading 1 pixel from the neurons, from the outputs of the previous maps, I'm reading entire regions. So for this to make sense, it becomes even more critical now that these maps are arranged in the same manner as the input itself, so that there's a one-to-one correspondence between regions in the maps of, say, the second layer neurons and regions of the input. Make sense? Okay. And so then our final output layer can be put through a softmax or what have you for does this have a flower? Now, so what has happened here? We haven't really changed anything. We are still scanning the input using an MLP. The only thing that is different now is that the MLP itself has a lot of shared parameters. So within the MLP, you have more sharing of parameters. And so we just sort of recurse the idea of a shared parameter network to even the subnets themselves. Questions? Right. I see all of you are falling asleep. Do you want a 1-minute break to go wash your faces or something? Yes, no. Raise your hands if you do. You may. Right.
I'll stay here.
Okay. It's just one person. Everybody on Zoom I know is sleeping. Nobody's answering. Okay. So it seems to be convenient. Yes. That's a wash your face alarm. Okay, Adru.
So when we are looking at the layers propagating, creating a square matrix, do we say that the dimensionalities of those matrices are with respect to the image the same?
So it's not, well, it's a matrix. I like to think of them as maps, right? So this map is proportional in size to the input, that's all.
So it's not the same, it's proportional.
It's proportional.
So can we calculate the dimensions with each layer?
So of course, right? If you're taking a step and at each position you're taking a step of 1 pixel, then the sizes are going to be identical to the input, except for some boundary effects, right? If the step is greater than 1 pixel, then the sizes are going to change. They're going to shrink. We'll see more of that in the classes, subsequent lectures, okay? And so what happened over here? Earlier, when we were not distributing the parameter across the layers, the pattern across the layers, you were scanning left to right, top to bottom, pulling out a segment of the image and putting it through an MLP. And so within the MLP itself, right, and if you rearranged it, each layer was scanning the input. But within the MLP itself, the first layer and only the first layer pulled out the segment of the input, a rectangular segment of the input. So that's for L equals 1, right? For subsequent layers, you looked at only 1 pixel from the maps produced by the previous layers. So this code actually became simpler when you distributed the parameters. what happened is that every layer is actually pulling out a region from the maps produced by the previous layers. So here, instead of having this if clause saying only the first layer pulls out a square region from the previous layer, and that subsequent layers are only reading 1 pixel from each of the maps of the previous layer, we are saying now at each layer you're pulling out a region from the maps of the neuron produced by the neurons of the previous layer. Is the distinction making sense? Ibrahim, is it? Okay, he didn't, but he has to nod. Yep. I can make out the completely lost face, and a lot of you have lost faces. You may ask questions, yes?
Is a slight typo, so the slide title should say with distribution, because now you're letting each subsequent layer take a region from the prior layer.
Oh, that should be with distribution, sorry. That should be with distribution, the title is wrong, you're right, yeah. Okay, so this business, okay, what I meant was earlier, if I had an image, the first layer neuron was looking at this region, right, and producing its map. A second layer neuron was looking at only 1 pixel from each of the maps, right? So I needed an if clause. If you're in the first layer, look at a square region. If you're in the second layer, you need to look at only 1 pixel. Now I've generalized. I'm saying if you're in the first layer looking at a region of the input, maybe this size, and if you're in the second layer, you're doing the same thing. So every layer is behaving identically to every other layer. So pseudocode-wise, it actually becomes simpler. That clarify anything at all? It didn't, okay.
All right, so I do have a question about my understanding, sir. So like basically like in the old canon, like what you said that you needed like the if statement because in the first layer you look at this like a giant patch of like the image, and then like everything else like after that is just like basically like processing like basically one value from each of the output maps.
Absolutely.
But the new canon, sir, is that like you look at a smaller patch in the first layer, but like in subsequent layers, like you look at a patch. You look at a patch from each of the output maps of the first layer in order to like get the maps for the second layer.
That's absolutely correct. And so what has happened? Yes, Spring.
This is when we say the shared parameter thing continues everywhere. So when it learns from the first layer, all of those have the same weight. All of those are shared parameters and it moves. So how will the network learn if the next layer also has identical parameters?
The rules for shared parameters didn't really change, right? So long as, even within this guy over here, all it means is that anytime I'm updating any one of these red lines, all of the red lines have to be updated. We just have to keep track of what is what. It becomes implicit, as we'll see in later classes, yes?
If we shrink the flower, if like the flower size is smaller, will it be caught up in like the earlier layers because like the sliding window is smaller as well?
So this is going to appear in your quiz. But the point is, eventually, this when you distribute the patterns, it becomes a little more resilient to changes in the size of the flower itself, but not as much as you'd like. You're not going to be able to see every possible size of flower, right? Eventually, it depends on how much on the data you throw at it for training, right? So any questions? Okay. This business of scanning left to right and looking for a pattern in a region, this is called convolution. So this entire network is called a convolution network. Now, convolutional neural network. Now, there's a little bit of terminology. Those of you who are from the electrical engineering department, I don't know if there are any over here. You're familiar with the term correlation versus convolution. What we just saw was a correlation, not a convolution. But it's terminology, who cares, right? Anyways, they are conceptually identical. So I have the same thing with vector notation. You can do the same thing for, the picture that I showed you showed us scanning a two-dimensional image. You can do the same thing when you're scanning for sound. Right here we were looking for flowers when I did this. If I were just listening for the word welcome, the process is pretty much the same if I use this vertical bar representation. The first layer is going to compute its inputs, its outputs at every position. And the first layer, so let's say I expect the word welcome to be this broad. then the first layer is going to be looking at the neurons are going to be looking at a smaller region of the input. So when I go to the second layer, I want the region of the input that's being analyzed to actually become slightly wider. So how would I do that? If I want the second layer to be looking at more of the input than the first layer, how would I do this? Anybody? Yeah. Yep.
Make the second layer read a patch of the input.
Right. So if the second layer must look at this wider region, it's going to actually have to look at a patch in the output of the first layer neurons, right? Now the third layer must, and so the second layer neurons can compute their outputs like so. And now if the third layer must look at this region, as before, the third layer must now look at a patch in the outputs of the second layer neurons. Is this illustration making sense, right? So this whole structure, it's the 1D scan version of the convolutional neural network, and you can have a final perceptron to aggregate the evidence. This is called a one-dimensional convolutional network, neural net. It's also called a time delay neural network for historical reasons, yes.
For like this type of network, it's like we are assuming the width of the welcome is known, but what if like the width is stretched, people say welcome in different continuations?
So when you actually distribute the parameters, somebody else asked this question as well, right? If you just had, if you didn't have distribution of parameters, you would be right? Because you're assuming that the width of the word welcome is fixed and it's about the size of the patch that's being considered by the first layer neurons. And if you wanted to have some diversity in the width that you can handle, you'd actually have to throw that into your training data. Once you begin distributing the patterns across layers, it becomes a little more resilient to changes in the size of the pattern that you're looking for. But even there are limits. Beyond a point, it's not going to work. Okay, here's the third poem. This is going to require 4 Pokemons. Guys, please reply. Jeffrey, be ready. Okay, someone answered the first one. So who's Noctowl? Is that
Noctowl.
Who's Noctowl? Okay, so we'll answer to the first one. Okay, is the first statement true or false? She doesn't know. Okay, well, let's hold that in abeyance. Let's ask about the second statement. Clefa? Who's Clefa?
Yes, sir.
Okay, what about the second statement, true or false?
It's true.
Okay. And who's Grumpig? Is there a Grumpig amongst you? No one's grumpy, okay. Okay, so what about the third statement, true or false?
False.
False, okay. Cacnea, is that right? C-A-C-N-E-A?
What?
C-A-C-N-E-A.
Oh, Cacnea.
Who's Cacnea? Okay, we're missing Cacnea. These names are fun. Kingdra, K-I-N-G-D-R-A. Who's Kingdra? Man, you guys are more absent than present. Kingdra's absent. Who's Meganium? M-E-G-A-N-I-U-M.
That's me.
Okay, last statement, true or false?
I think it's false.
Let's check, right? Non-distributed scanning requires the output maps to be arranged in the same shape as the input. It doesn't need to be because you're not looking at regions, right? You're picking up pixels. If you have some kind of an index which tells you where everything is, you're fine. Non-distributed scanning does not require the output to be arranged in the same shape as the input. It's just the reverse of the first statement, right? Distributed scanning requires the output maps to be arranged in the same shape as the input. Obviously true, because you're sort of building on the maps. You're looking at regions of the map, and that's how you're building the pattern. So the cost of distributing the pattern is that now you have to maintain the shape, and you have to make sure that the maps that you get are somewhat proportional in shape in size to the original input. So continuing on, why bother to do this? Why do we distribute? There are about 3 reasons. First, distribution forces hierarchical representations with localized patterns and lower layers. This is more generalizable, yes?
Can you explain again why in non-distributed scaling the size does not have
the shape? And non-distributed scanning, if I just said, 1, 3, 9, 2, 7, 6, if my indices were just in any arbitrary order, so long as I knew what the indices is represented, I'm fine. Right? I don't need to keep them as a rectangular patch. I could just arrange them in vertical rows and I'm fine. Does that make sense? Okay. So anyway, so distribution forces hierarchical representations with localized patterns and lower layers. Requires fewer computations because we reuse computations from lower layers and we need far, far fewer parameters. Let's see how. Let's look at this first thing. Why does having hierarchical representations make things easier? We know this already. So way back when we were looking at the double pentagon, we saw that if we wanted to do the entire double pentagon all at once, you required an absurd number of neurons, right? Whereas if I distributed the pentagon across many layers, the first layer just found all the boundaries. The second layer found the subshapes, the 2 pentagons, and then the third layer found the entire double pentagon. This made the whole process so much more simple and so much more generalizable, right? Same thing, if we were trying to recognize digits, you want the first layer to find the individual components of digits, the second one to actually find the digits, and then finally you can say, is there a digit in this picture? When you distribute the pattern across the layers, the model becomes more robust and has far fewer parameters and becomes more generalizable. So this is something that we're already familiar with. The more interesting question is this: fewer computations and fewer number of parameters. How does that happen? So for this, I'm going to look at this one-dimensional scan example as my base case. So I have this sequence of vectors. Let's say each vector is some d dimensions. Each little bar actually represents a vector. And let's say I want to scan this input for a pattern that typically is 8 vectors wide. And so the network over here is what we have. We have a 3-layer network with 4 neurons in each layer, right? In my illustration. So the actual computation is going to be this entire network, analyzing the input 1 position at a time. And for my illustration, I'm assuming that the network is striding by 2 vectors. So after having analyzed the input at some region, it's taking a step that's 2 vectors long and then repeating the computation, okay? I'm not actually going to show those little yellow balls. I'll just show bars because those dots are present inside each bar. And this is the illustration we will use, okay? Furthermore, now let's consider the case where I don't have distribution of parameters. If I don't have distribution of parameters, this entire network is analyzing the entire that entire region of the input. If I have n1 neurons in the first layer, n2 in the second layer, and n3 in the third layer, and say it's this guy, these vectors are say d dimensions wide, then the total number of parameters I'm going to require is 8 times n1 times d for the first layer. Make sense to everybody? Right. What about the second layer? How many parameters would I need in this case? You're saying? How many would I need? Guys, wake up, please. N1 times N2, because you have N2 neurons each connecting to N1 neurons, right? And what about the third layer? How many parameters would this guy need? N2 times N3. You have N3 neurons each connecting to N2 neurons. So, the answer's on the slide, so you have to be a little more awake. Okay. This is easy, okay? And so the same computation is going to be performed all across the input. Now let's consider a situation where I'm distributing the same pattern, but then I'm distributing the pattern over 2 layers. So I have this first layer neurons, which are only looking at 2 time steps. And they are scanning the input, looking for patterns that are 2 time steps wide, right? And the second layer neurons are now going to be looking at 4 of these outputs simultaneously. So you can see why having them have the vertical representation actually makes sense over here, right? It shows me that those 4 guys are all at the same time. So what is the width of the input that the second layer neuron is now considering? Anybody? How many? Yes, you're saying? What is the width of the input that the second layer neuron is considering? Yes. Can you say that aloud, please? 8, because it's looking at 4 first layer neurons, the outputs of the first layer neurons at 4 positions. Each of those is looking at 2 inputs. So the second layer neuron is now looking at 8 inputs. So this network is analyzing an input which is the same width as the previous non-distributed network. Make sense? Okay. But now let's consider the differences in parameters, right? So if I have N1 neurons over here, N2 over here, and N3 over here, how many parameters would I need in this case? Anybody? Someone? Yeah.
It would be 2D times N1 in the first layer.
Exactly. It's going to be 2D times N1 in the second layer. What about the second layer?
4 times N1.
4N1 times N2 plus N2, N3, right? Now, so because those are all the parameters we have. Now, if I have a second network which has exactly the same number of neurons as this guy, then the first layer must have 4N1 neurons because I want the same number of neurons, right? It's the same complexity of parameter, of the network in terms of neurons. So that means how many parameters will this guy need? It's going to be 4N1 times 8. So that's 32D_N1 for the first layer, plus 4N1, N2 for the second layer, plus N2, N3 for the third layer. Basically, what has happened over here is that each one of these 4N1 neurons has its own set of parameters, whereas here, I'm making 4 identical copies of size N1, and I need to compute the parameters for only one set. And so you can see that the size here is the actual difference is 2D_N1 versus 32D_N1. There's a factor of 16 that has suddenly emerged simply because I shared the parameter, distributed the pattern across 2 layers, right? I could do the same thing across, so we are reducing the number of parameters. What about computations? In terms of computations, these first layer neurons scan the input, and this second layer neuron is going to be looking at 4 of these guys, right? Now at the next position, if I scan using the same MLP, this second layer neuron is going to be looking at these 4 elements. So is there any computation that I performed when I was analyzing the first block that can be reused for the second block? Can you identify it? What do you think? Do you see it? Right? Those guys, right? These common ones are going to be reused, right? And so at each position, you keep reusing some of the computation. And so the higher level neurons reuse some of the computations performed at the lower levels. So 2 things happened. First, you needed far fewer parameters, orders of magnitude fewer parameters, and then you're performing much lesser computation because you keep reusing things. And this is when I distributed across 2 layers, right? If I distribute it across 3 layers, here's something. These guys are scanning the input 2 inputs at a time. These guys are scanning the output of the first layer 2 inputs at a time. And the third layer is scanning the output of the second layer 2 inputs at a time. But this network is also looking at an input that is width 8, right? And how many parameters will this need? This is going to need 2D_N1, right? Plus this is going to need 2N1, N2, and that's going to need 2N2, N3. So this size is going to be even smaller than what we had before, right? Just for comparison, those are all the unique parameters in the network. And if you compare it to what we had earlier, you had 32D_N1 plus 8N1, N2, if assuming both networks have the same number of neurons, and you can see how much the difference can quickly grow, right? This makes sense to everybody?
Yes.
Right. And then once again, you can also see that this when I distribute it across multiple layers, you can see how the computations can be reused. I'm reusing the first layer computations at different positions, but now I'm also reusing second layer computations, right? So all of those are being reused. Actually, here's a picture where the scanning MLP has this structure. And if you look at what happens when you scan the input, you can see all the first layer computations and the second layer computations get reused. So you get a much lesser computational overhead in terms of scanning for the input. Okay? So just a rhetorical question, we don't have time for this. The same thing happens even when you're looking for analyzing two-dimensional inputs. So here, say I'm scanning a 4x4 input, right? And I'm taking a stride of 1. Can you identify the regions that are being, where I can reuse the computation in this picture?
Yeah.
Right. So the overlap regions can be reused, right? So
Overlapping regions.
yeah. And also in terms of parameters, if I'm trying to look at a k cross k block of the input, if I don't have distribution, the first n1 neurons are going to be looking at k squared n1 parameters. The second one is looking at n1, n2. The third is looking at n2, n3, and so on. Whereas if I distribute it, and so the first neuron is going to be looking at k0 squared n1. The second guy is going to be looking at, k1 squared n2, and so on, right? So again, the number of parameters, if you ensure that the total number of neurons is the same in both cases, the distributed version actually ends up needing far fewer parameters. I'll let you go through the slides to convince yourself, but in my trivial example, when I'm looking at a 16 cross 16 region of the input, my non-distributed network requires 1,034 weights. The distributed one requires 194. You can see that it's a factor of 5. This difference can grow. It can actually have a factor of 100 or 1,000 in difference between the distributed and non-distributed versions, even more. Okay.
And you're saying this for the forward pass?
Yes.
Okay.
But these are the parameters, right? So that's the size of the network. The network just has far, far, far fewer parameters. That's it. Because I distributed the patterns over several layers. That answer your question? Okay, so distribution forces localized patterns. It reduces the number of parameters by huge amounts, and also you get significant gains in shared computation. So the key intuition, regardless, is that regardless of whether you're distributing the patterns over many layers or not, eventually what we are doing in every single case is scanning the input for the target pattern with an MLP. All that distribution did was to change the shared parameter structure of the network. That was it, right? So the story so far is that position invariant. So Ryan, can you flip your phone? Thank you. So position invariant pattern recognition can be performed by scanning the input for a target pattern. Scanning is equivalent to composing a large network with shared subnets. The operations in scanning the input of the full network can be reordered as scanning the input with individual neurons in the first layer to produce scan maps of the input, jointly scanning the maps of outputs by all the neurons in the previous layers by subsequent neurons, and the scanning block itself can be distributed over multiple layers of the network, resulting in significant reduction in the number of parameters. A final poll before we wrap up. Pidgeot? So who's Pidgeot? P-I-D-G-E-O-T.
That's me.
Okay. First statement, true or false?
True.
Okay. Who's Shuppet? S-H-U-P-P-E-T. Shuppet's missing. Who's Manectric? M-A-N-E-C-T.
Manectric.
Manectric. Yeah, that says mandatory.
I think the second one is true.
Okay. The second one, true or false? Okay, guys, just tell me, what about the second statement? Is this true or false?
True.
Third one, and the fourth. Okay, the fourth is false. Because just because you shared the parameters or reused terms doesn't mean that you compute fewer variables. In terms of the intermediate terms that you store, it's just going to be the same number, okay? Some final touches, terminology. So these guys, first, the entire operation can be redrawn as maps of an image. So one way to look at it is that the first layer neurons, each first layer neurons is looking for a specific pattern, maybe a sepal. Then it's repainting the input, except that in the process of repainting the input, it's going to highlight regions that it sees where it finds the patterns that it sees. The second layer neuron, again, is going to be repainting the input by scanning the outputs of the first layer neurons, but in doing so, it's going to highlight the patterns that it sees, and so on, right? So you can think of each layer of neurons as creating a map where it's basically redrawing the input with the patterns that it's looking for highlighted. So these sets of weights for the scanning neurons are generally called filters, or also called kernels. And the number of neurons that you have in each layer is often called a number of channels. And the size of the input that each neuron looks at effectively is called its receptive field. So the receptive field for the first layer neurons over here is going to be this small region here. The second layer neurons is going to be this larger region. The third layer neurons is going to be still larger regions. For the first layer neurons, the size of the receptive field is obvious. It's just the size of the pattern of weights that it has. For the subsequent layers, you've got to calculate it by accumulating across layers, right? And then there's a term that's often, which they call flattening, where they just, when you finally don't need to maintain the shape of the maps, you can just sort of unravel the maps into a single vector. And so that's called flattening. It's a term that you're likely to encounter. And last but not the least, actually not quite the last, as it scans, it can scan, it can move forward by one step or a step that's larger than one. So the size of the step that the neurons take when they're scanning the input is called a stride. If the stride is 1, it's not going to change the size of the maps. If the stride is greater than 1, say 2, it's going to shrink the maps, right? Some pseudocode. And then we also like to account for jitter. I'm composing petals and sepals into a flower. But if one of the petals moves a little by 1 pixel, does it suddenly stop being a flower? It doesn't, right? So to account for this thing called jitter, we have an operation called pooling, where we typically look at regions of the input and then pick the largest value. We're going to see more of these in the next class. And so, and there are various kinds of pooling. And so here's the overall structure. It's called a convolutional neural network, which includes convolutional layers and the occasional pooling layer. Some examples. So here's to wrap up. Here's the story so far. Just the final thing. Neural networks learn patterns in a hierarchical manner, simple to complex. Pattern classifications such as, does this picture contain a cat, are best performed by scanning for the target pattern. Scanning for patterns can be viewed as classification with a large shared parameter network. Scanning an input with a network and combining the outcomes is equivalent to scanning with individual neurons, layer-wise. And the scanned blocks can be distributed over multiple layers for efficiency and generalizability. And for 2D or higher scans, this is a convolutional network. For 1D scans, this is often called a time delay neural network. So that's it. I will see you in the next class. Thank you.